まだあと5分なのかな。なんかまだ始まりそうになるんだけど、ここでやろうか。台風来てんのね。Okay, so I'll talk about the opera experiment. So I think almost all of you are very familiar with this experiment. So, okay, first, the purpose of the opera experiment is, of course, the search for new mu, new tau oscillation in appearance mode. And the distance, the baseline is 730 kilometers from CERN to Gran Sasso. And also, the new mu nu e is our target. The nu tau is expected to seen like this. The interaction happened, and we can detect the tau track, and the tau can decay in short lengths like this. And our purpose is detecting this decay point and confirm the tau. Okay, so here just a review of emulsion in neutrino physics. So the first one was the E531. So this is aiming to measure the charm particle lifetime. And also, so the E531 reported the first result upper limit of new mean tau oscillation. And the target mass is 100 kilogram. And then the chorus experiment was planned and done. The chorus was, the main purpose is the new mu tau oscillation. And also charm physics, they gave a lot of results. And the target mass is 1 ton. And parallelly, the donuts experiment was going. So this is the purpose is the first observation of new tau and confirm the capability of detecting new tau interaction. And the last is the opera experiment. Of course, the main purpose is this oscillation. And you can see the target mass is much bigger than previous. And this is the biggest emulsion experiment ever done. And also for the number of countries, institutes, and researchers, I think the number is biggest in emulsion experiment history. Okay, the beam is called CNGS, and here it's written the spectrum of new mu. And the average energy is 17 GeV, and the interaction, the contamination from other neutrino is for electron and anti-electron neutrino 0.87, and for anti-muon neutrino 2.1%. And of course, the prompt new tau is negligible. Okay, the opera detector outlook is like this. So we have two parts called the super module 1, 2, and the super module is composed from a target part and muon spectrometer part. And in the target part, there is a ECC, emulsion cloud chamber, and the target tracker composed from scintillating strips. And this is the opera emulsion cloud chamber. The ECC is composed from 56 dead plates and 57 emulsion films. The total weight is 8.3 kilograms. And we used in total 150,000 bricks. And this is corresponding to 1.23 kiloton. And of course, to make this kind of large amount of bricks, we needed the automatic assembling system called the BAM. And this is a picture of the BAM. So they produce the bricks, putting dead plate film in dark room. And the capability is around 700 bricks per day. And this is the opera film itself. So the film was made by Fuji Corporation, and here is the cross section of the film. It has 200 microns base, and both sides the 44 microns emulsion were poured. So this pouring was done by automatic machine by Fuji company. And this is a picture of the crystal. and the crystal size is very tuned, and the intrinsic resolution is around 50 nanometers. And the grain density for MIP is around 30 for 100 microns. And also for, after the ECC, we put called CS films. The CS is composed from 2 films. And changeable sheets. And why we need this? This is because, so Opera Emulsion is, has one new thing compared to the old experiment. What is the Opera detector has TT after the emulsion, and if the interaction happened in ECC, then we can detect where the interaction happened, and in real time we pick up the ECC and directly go to development and analysis. So this is somehow a semi-real-time experiment. But sometimes the ECC is difficult to be decided like this. So in this case, first we check the CS, and if the track is confirmed in a CS, then finally we can extract the ECC, then develop and go to analysis. So to choose the right bricks, so we used the CS film. And this is a target tracker composed from scintillator strips. And this is a brick manipulator system to pick up the target ECC. This drum stores the ECC, and this mechanics will put and back the bricks. And also for the developing, the amount of develop is so huge. So that's why we need automatic developing system also. And the capability is around 20 ECC per day. Okay, and for analysis, we developed the automatic scanning system here in Europe and also in Japan. And the speed is here, the 200 square centimeter per hour. Okay, then I explain about the procedure of the location. So first, the CS was scanned, and if the track was found in ECC, then the brick was extracted and developed and start the analysis. And so we do the called scan back for this track. And if the track was stopped in ECC, then we judge the track was starting from this point and do the volume scan around the stopping position. So this is called the total scan. And here the result, the detected tracks in a volume scan. And after rejecting penetrating track and searching the vertex position, then we can find the clear vertex in the volume. And here is the status of the analysis from the beginning of the experiment. So we started 2008, and the number of extracted and the number of CS scanned and number of CS track found and ECC scanned, and this is the number of interaction found in ECC, and this is the number of decay searched event. And so far the total number is around 6,300 located, and around 5.5 kilo events were decay searched. And here is a very famous event, the first neutral candidate. And here is the vertex position, and here the very short wet track is the candidate of tau track. And this track is decaying into hadron, and also we observed gamma ray. And this was confirmed as tau neutral interaction. Display of total detector. This is the X view, and this is Y view. And here is some kinematics version is shown. And here I have to explain about the techniques to measure the momentum by multiple Coulomb scattering. So in ECC, we have 1 millimeter thickness lead plate sandwiched with emulsion. So we can use the scattering, the amount of scattering between two films. Then we can deduce the momentum of the track. And this is the real data, the comparison between muon spectrometer and the multiple Coulomb scattering. And here is the resolution of the momentum measurement is shown. And then next, the second candidate was found, and also the tau is wet color track. And in this event, the decay was 3 prongs, 3 hadrons. And this was also confirmed as a tau candidate. And here the kinematical value is shown. And rather recently, the third tau candidate was found. So the vertex is here, and the tau candidate is decaying into muon in this case. This is the detector view, and here you can see clear muon in target region. So this is a summary of the nu mu nu tau oscillation analysis. So far we found, we confirmed 3 tau candidates, and one is tau 2 hadron, and one is tau 3 hadrons, and the other is tau 2 mu. And so far the significance of non-null observation is 3.4 sigma was reached. And also the nu mu nu e is our target. Okay, so this is one candidate of electron-neutrino interaction. So this is a interaction point. So you can see 3 prongs, and one track is creating an electron shower. So the ECC has electron identification capability. So here is the view of the last this event, and here you can see a clear shower in 4.1 cascade length. And first, we should check the very first position of the track, because if the track is electron not from pi 0 gamma, so if the electron is coming from pi 0 gamma to electron pair, then you can see 2 dots like this. So first, we should check the track is not composed from 2 points, just a point. So then we can eliminate the gamma to electron pair. Okay, so we have analyzed for 2008 and 2009 data sample, and from 5 or 5 zero events, we have so far observed 19 electron-neutrino events. And here is the spectrum of the found events, the dot, and also showing the contamination from the prompt beam is shown. And the result is the expected number of background event. The contamination is this number, and the observation is 19. So the result is observation is agrees with background expectation. And this gives the upper limit of the theta 13 of 0.44 at this value of delta M13 square. Okay, the summary is the OPERA experiment is successfully collected data from 2008 to 12, and also the analysis is still going on to increase the statistics. And total number of POT is around 18.10 to 19 is integrated. And for new mu tau oscillation, so far 3 events were observed and confirmed, and the significance is 3.4 sigma. And also for new mu e, we have published one paper, and we have set limit on theta 13 less than 0.44 at 90% confidence level. Thank you.
難しいな。ポケットでもいいのこれ。
動いてない。
いいの？
これが使える。
これが使える。これでいいの？でこっちは。
いいんで、これで置く。
これで送る。はい。My name is Shibuya of Toho University. I like to talk about emulsion neutrino spectrometer for future neutrino experiments. First, I like to show you past emulsion experiments for neutrino oscillation study. Then I like to introduce our emulsion neutrino spectrometer, conceptual design, and also test beam experiments. Then we had practical problems, so how we will solve, and last, future prospects. これどうするの？これではいかない。こっちか。OK、ありがとう。First emulsion experiment for neutrino oscillation was Fermilab E531. Main purpose of this experiment was measurement of charmed particle lifetimes. We made measurement of diesel lifetime, diesel, and D plus minus, and D sub S, and lambda C is separately. And during the experiment, it was noticed that emulsion is also suited for detecting tau lepton decay and new tau charged current interactions. So, yeah, because tau lepton has a short lifetime as charmed particles. This is a exclusion plot, mixing angle and delta m squared. This is a boundary, excluded region. It's here, shown here. It was obtained based on about 4,000 neutrino interactions. About 10 years later, this region was it was found that this region was very interesting because if new tau is a candidate of cosmological dark matter, neutrino oscillation could occur this region. So we intended to extend this sensitivity like this. Chorus experiment was designed and performed. Data taking was done in 1994 to 1997. Based on about 1 million events, we have set this limit. Unfortunately, no candidate was found, so limit obtained. This is a donuts experiment. This is not a neutrino oscillation experiment, but a very important first observation of new tau. Beam dump experiment at Fermilab. In total, 9 new tau events are observed. This experiment firstly used ECC. ECC had a repeated structure of 1 milli-thick stainless steel plates interleaved with emulsion films. yeah, tau decay is clearly seen here. This is an opera experiment explained by previous speaker Kawada-san. So I skip. Okay. I like to say in this slide, in opera experiment, we can identify a neutrino flavor. Nu mu charged current interaction can be identified, and nu e charged current interaction is observed here, like this, and nu tau interaction is also identified like this. Three events found so far. To date, about 600 events are located, and about 5,000 events decay search finished. The third candidate is tau goes to mu decay. Mu can travel long distance, and charge of the muon was measured in the magnetic field. So it was found to be negative. So the oscillated neutrino is nu tau, not nu tau bar. So charge sign measurement is very important. So what is next? Let's consider a future experiment. Traditional neutrino beams contain a nu mu bar with small admixture of nu e bar. And neutrino factory muon storage ring offers nu e, nu mu bar, and nu e, oops, this one, mistake, bar. Anyway, in any case, mixture of different flavors or neutrino, antineutrino. So a detector which can identify all the neutrino flavor is strongly required. So emulsion neutrino spectrometer. In future neutrino oscillation experiment, it is essential to identify the incident neutrino flavor and also to distinguish neutrino interactions from antineutrino interactions. Nuclear emulsion detectors can identify the neutrino flavors, nu e, nu mu, nu tau interactions as clearly demonstrated in donuts and opera. The emulsion neutrino spectrometer will add a new capability to distinguish neutrino interactions from anti-neutrino interactions. It is accomplished by measuring the deflection of produced lepton in a magnetic field and determining the sign of its charge. I will talk about its conceptual design and performance test and future prospects. Oops. Emulsion neutrino spectrometer is mainly composed of two parts of emulsion detectors. One is emulsion cloud chamber here to provide a massive target and also to identify secondary particles. The other is spectrometer part here, to determine the charge sign. In principle, three emulsion films are spaced with each other by a certain distance of less material region and placed in a magnetic field. The sign of lepton charge from a charged current interaction can be identified in the magnetic field. Emulsion spectrometer part. Charge sign is determined by measuring the sagitta, this distance, of charged particles in the spectrometer. This table shows you, in case of 0.5 GeV charged particle, it gives a sagitta of about 80 micrometer. And 1 GeV charged particle gives about 40 micrometer. And 2 GeV, 20 micron. It is very easily measured in emulsion. A test for an emulsion spectrometer was performed at the KEK. The beam momentum was set for 0.5, 1.0, and 2.0 GeV with a relative spread of delta P over P of 5%. T1 beam line. Test beam experiment. This is a thin emulsion spectrometer design. This part, there are films and spacer here. This is a spacer. This is a real photograph. The spacer is a vinyl chloride plate which has a hole of 40 millimeter by 40 millimeter at the central part. And sagitta is the same. This is a magnet, compact permanent magnet used in the experiment. Halbach type magnetic circuit. And yeah, this is a photograph. Inside, about 1 Tesla of magnetic field is produced. The uniformity is very good, less than 1% inside the central part. This is a result. Two-dimensional sagitta values of 0.5, 1.0, and 2.0 GeV charged particles here. This is a center sagitta X component, one component. This is a reference. No magnetic field, pi plus was exposed. And 2 GeV pi plus beams and 1 GeV pi plus, 1 GeV pi minus, and 0.5 GeV pi plus, and 0.5 pi minus. This is a sagitta X projection, pi plus, pi minus, 1 GeV, pi plus, pi minus, 2 GeV, pi plus, pi minus. Yeah, this is a table of results. You can see the measured value is good agreement with expected values. Linearity is very good. This is a beam momentum. Vertical axis is sagitta. This is a reconstructed measured momentum distribution. And this figure shows momentum resolution. Error due to multiple scattering here, constant term, and error due to track resolution like this. Momentum goes up and error increases. And total error is like this. During the experiment, some practical problems are found. One is deformation in emulsion was produced in the development process, which must be corrected. Second, slip of emulsion films during the exposure are observed in some cases. And flatness of emulsion films are not complete. That is also a problem. First problem, deformations in emulsion, which was produced in the development process. Method of correction. Major part of the deformation in emulsion originate from development process. Typically, these deformations are of the order of 1 micron in the center part. That is okay. Tolerable deformation, but at the edge part, 10 to 20 micron deformation are produced. So that is a problem. By printing on each film before development a set of accurate reference marks, these deformations can be determined by comparing the measured position of the marks to their nominal one. By this technique, the whole area of an emulsion film will become a position detector with 1 micron accuracy. This figure shows film deformation. This is 5 micron, so edge part very big, about 10 or 20 micron. That must be corrected. Photomask was used to correct deformations. The photomask is made of synthetic quartz with a small thermal expansion coefficient of 5.8 times 10 to minus 7 per Kelvin. Grit mark was printed over this area. We used a contact printer equipped with a vacuum pump and an electric flashlight. This is a printed image of 5 micron grit mark. This is a design pattern of grit marks on photomask. So we carried out a muon beam exposure of an ECC brick at CERN in 2007. ECC brick was exposed to 30, 40, 150 GeV muon beams. And this result shows residual track position. We connected and reconstructed the beam tracks. And residual track positions as a function of distance from the film center. Film center is okay, but if we go to edge part, the residual become larger. But if we correct with photomask, residual remain smaller. About this area, position measurement accuracy of 0.6 micrometer obtained. Second problem, slip and bending. If this screw one tighten the screw strongly, the film bent. And if we tighten the screws weakly, film slip. This is evidence of film slip. And this is evidence of film bending. It is not very good. So we devised a new structure of emulsion spectrometer was considered. We use spring. Films and spacers are fixed by springs which give a constant and uniform pressure. This is springs. So again, test experiment was performed at CERN. This was done last year. This is a spring number, and this is a strength of spring. Yeah, various strengths spring was tried. This is 4, 8, 12, 20, 40, 80 Newton springs are tried. This is a beam exposure condition. We applied two actions or shocks to the emulsion stack. One is a soft shock. Insert it into the magnet hole and put it back. That is ordinary stack handling, chamber handling. And second one is a hard shock. Drop it on the table from the height of 3 centimeters. This is a hard shock. The result, before result, going to result. First exposure with theta equals 0 radian. That means beam was exposed to the film perpendicularly for alignment. Then action 1 is applied, soft shock, inserted to the magnet and put it back. Then secondly, exposure with theta equals 0.1 radian, tilted a little bit. Then action 2 is applied. Drop it from the height of 3 centimeters, hard shock. Thirdly, we exposed the ECC to the beam with theta equal minus 0.1 radian. As we can discriminate 3 beam tracks from each other, we can separate the effect of action 1 and 2. Results of the test beam exposure for soft shock, spring strength greater than 40 and 80 newtons, that is okay. Displacement remains within 1 micron. But hard shock, no good. So we must avoid hard shock. And flatness of films is important to use emulsion films as a position detector. Film in the past experiment. This is in this experiment, emulsion was almost flat. Film flatness has been much improved by using plastic support and springs which produce uniform pressure. Conclusions. The emulsion neutrino spectrometer has a potential to become one of main detectors in future neutrino experiment. Concept and fundamental performances were successfully demonstrated by a test beam experiment. At the same time, some technical problems were found. By investigating their causes, some solutions have been found and they have been confirmed by test beam experiments. It's time to start the next move. So outlook. The next subject of the emulsion neutrino spectrometer development will be nu-E bar identification. Nu-E identification in emulsion cloud chamber is being well studied in OPERA. Nu-E bar separation in emulsion neutrino spectrometer should be studied. Some tests and demonstrations are clearly needed. For example, the near detector hole of J-Park might be a good place to install the emulsion neutrino spectrometer to study low energy neutrino interactions. This is already Kawada-san shows. So anyway, if we put this region, emulsion spectrometer, and in a magnetic field, we can measure the charge sign of electron. Then we can discriminate neutrino from antineutrino. This is a neutrino experimental facility at J-Park. This is a target, and this is a near neutrino detector. So distance is 280 meters. This is a beam spectrum. 0, 1, 2, 3 GeV. 0 on-axis beam is like this, and off-axis is like this. So 1 or 2 GeV beam. And this is a beam composition, almost pure nu-E beam, but some contamination of nu bar, and 1% nu-E and 0.1 nu-E bar. So we like to measure or discriminate this one. This is a beam intensity. From this, we can expect in the near future, 10 to 21 POT per year is expected. That means 170 kilo events per ton per year is expected. So approximately 10 to 3rd new mu event per brick per year is expected. So brick per brick, 10 new E event and 1 new E bar events are expected. That's all.
Yes. May I ask you slide number 20 about distortion problem?
Yes.
20. No, next.
Next one.
Next.
Okay.
Thank you. Sorry, maybe technical question. How you prepare such kind of grid? How you light in hole? How you prepare hole with so small size? Because you write that dark pot will have size 15 microns up to 15 microns. 15? 15 microns. How? In case if you make some hole in any subject line.
No.
Sorry.
No. This is a mask.
Mask.
Yeah. Photo mask.
Photo. Yes. Understood.
So not hole.
Photo.
This is a metal.
Metal?
Metal. Later, I will show you.
Okay, thank you. Because it's a serious problem, and the smaller each pot, you will have enough.
This is very good.
Oh, okay. So, thank you.
Later, I will explain.
Thank you.
Yes.
You pay so much attention to establishment of neutrino flavor, but do you believe that factories of pure electronic neutrino can change situation? Is it useful? Is it scientifically useful to have neutrino, electronic neutrino factories?
Yeah.
Yes, you do see.
Yeah.
Electronic, pure electronic. In this case, pure electronic neutrinos.
Yes.
And this somehow solves the problem. The determination of new electronic neutrino. As I understood, you have been cocktail of muonic and electronic neutrinos.
Yes.
And you want to separate.
Yes.
But in the future, there could be appear purely electronic neutrino beams.
Purely electron beam?
Beams.
No, it's impossible.
Why?
You can make it.
Yes.
Beta beam?
Да.
Yeah, beta beam is okay. Yeah, of course.
Electronic neutrino beams.
Yeah.
But energy.
Yeah. Beta beam is okay, but other ordinary this is a mistake, but most of the considered beam, future neutrino beam has a contamination. So we need to separate.
I just want to mention that there is
You
implementation, there is
you mean beta beam?
you have
I
radioactive nuclei, multi-GeV radioactive nuclei, helium-6.
Yeah, that is a possible. Yeah.
And you are
Oh,
paying
only
but is it
pure,
scientifically
yeah.
satisfying?
Yeah. That is okay. But you use your ordinary beam, consider the beam is like this. So we have to separate the flame. That is what I